Once a star is lit, a new activity of nuclear synthesis can begin. It is the synthesis of type billiards.
Now, at the macroscopic level, as the coat of newborn stars mostly contains hydrogen and deuterium, they organize themselves into molecules into the atmospheric corona of the star. And like the giant planets charged with hydrogen as Uranus and Neptune, these molecules thus show a blue color. That's why the young stars are called blue giants, as is the case for example Pistol Star. Now look what happens to the stars after their first ignition. With the heat released by the first nuclear reactions, the original sheets will disintegrate into a multitude of individualized nuclei. The organized spin fields then give way to an immense stellar billiards, where the nuclei clash at random.
At this level, it is necessary to complete the description of the isotopes of helium and lithium in order understanding the nucleosynthesis of small nuclides. And let us insist that helium-4 is indeed the most solid nuclide of matter because the dodecahedron is the perfect form of order 5. Besides, this strength is confirmed by the phenomenon of alpha radioactivity, which shows that helium-4 is so strong that it remains individualized even within large nuclei. And this dodecahedral morphology is so strong that it can withstand gaps in the wall, which then gives the isotope helium-3. Isotope which is also a stable nuclide such as helium-4.
And again more, this stable five-fold structure can also align dodecahedrons between them without constraint problems. And this is the case of lithium, which includes two dodecahedral bases together.
With lithium-7, we have 3 times 7 pentagons, and therefore 2 bricks of 10 pentagons, with a central pentagon,
and 2 parietal gaps at the ends.
This makes a total of 21.
Regarding the structure of lithium-6, it is composed by the combination of 2 helium-3 partners at a parietal gap.
Of course, with this stable dodecahedral link, we can continue this dodecahedron succession in long column. And that's what we'll find later in heavy atomic nuclei.
But in smaller nuclei, fast rotation causes the column to eject terminal dodecahedra by centrifugal force, which limit the growth to lithium.
Now, the high rigidity of the dodecahedral structure requires short periods of life in heavy isotopes.
But one can observe that good symmetrical morphologies allow prolonging their lives, insofar as they are well balanced. Thus, with the addition of triple helix, the 5 and 7 helium are very unstable while helium-6 and 8, well balanced, have lifetimes of the order of 1 second. In such cases, as these nuclei vibrate in a larger volume, hence they diffuse a sort of halo during their observations.
The same logic applies to heavy isotopes of lithium. and due to the dodecahedral stiffness, we see that the lithium-11, very elongated, then takes the appearance of a peanut.
Now, let's back to the notion of spin. We can see that helium-4 possesses a null spin with its perfect symmetry.
And on the other hand, helium-3 has a dissymmetric morphology which gives it a non-zero spin value.
And now that we have reviewed the small nuclides, let's go back into the star's mantle during the synthesis billiards.
Under these conditions of permanent shock, only the strongest nucleus will survive. It is therefore helium-4 which presents the perfect morphology of order 5 in regular dodecahedron which will triumph. And it is this particular morphology that will enable it to withstand all internuclear shocks. Now complete the list of intermediate elements. We saw hydrogen and deuterium created during the initial synthesis of the Big Bang. Then, thanks to the action of the spin fields, it was the tritium with the heavy isotopes of hydrogen and helium-3 which appeared in the heart of the blue giant stars by friction effect. But also we discover the neutron, which reveals itself as the most active intermediate of small elements. It is a zero spin with a mass equivalent to the proton, as well as a very short lifetime, of the order of 15 minutes, transforming into proton with emission of various particles. Under these conditions, the neutron is therefore a kind of flat proton, with the three hypocycloids then evolving in the same plane, hence its zero spin. Since it does not have a locking ring, it rapidly returns to the proton morphology on the basis of three planes. But above all, it will associate with other elements like the hydrogen nucleus to give deuterium, with deuterium to give tritium, then heavy and unstable isotopes of hydrogen, with helium-3 to give it tritium with a proton. But again, with helium-4 to give heavy and unstable isotopes of helium. Therefore, the neutron is truly the most powerful and responsive nuclear building element. And consequently, all the nuclear activity of the small elements amounts to synthesizing helium-4. The energy released then originates in the surface reduction of the volutes of the cycloids because of the dodecahedral morphology. Knowing that the mass is related to the surface isolated by the cycloidic scrolls, the passage from the U-shape to the V-shape gives the star an enormous amount of energy according to the formula E equals mc2. Now let's see why the stellar activity remains blocked at this stage of helium-4 synthesis, especially in our Sun. We have just seen that small nuclides associate to give helium-4. But beyond this, nucleosyntheses are blocked for two reasons intimately related to the morphology of order 5. First, the billiard synthesis is very destructive because of the internucleus shocks and the powerful radiations coming from the nuclear transmutations. If a nucleus appears beyond helium-4, such as lithium for example, it is destroyed rapidly. On the one hand, with the arrival of another nucleus that will separate the two elements. On the other hand, with the penetration of irradiation through a parietal gap, which makes these small nuclei very fragile, despite their basic dodecahedral structure. Thus, although lithium-6 and 7 are stable nuclei in a quiet and cold environment, they have a very short lifetime in a universe as perturbed as a hot star in the synthesis phase of billiards. Now the other limitation of nuclear growth is caused by the instability of beryllium-8, which is related to the quinary morphology. It is then easy to see that the assembly of 24 pentagons in 3 lobes presents very fragile connections, which leads to a lifetime of less than billionths of a second for beryllium-8. Now, with 3 other inner helix pentagons, we obtain the beryllium-9, which is stable in a calm and cold environment, but which will undergo the same survival problems as the lithium with its parietal gaps. We can also point out the nucleus of the boron, which does not present any gaps, but which will also undergo the shocks of other nuclei linked to the fragility of its trefoil morphology. To sum up, we can say that during the billiard synthesis the star behaves like an immense shaker. There is a mixture of the small native nuclei such as hydrogen and deuterium that come from primordial galactic clouds, with the small intermediate nuclei such as tritium, helium-3, or neutron, or with the first medium elements such as lithium-6 and lithium-7, or else beryllium-9, or boron-10 and boron-11. And all this small world will then pass into the stellar shaker to give exclusively helium-4, which represents the most solid pentamorphology structure. Thus, little stars, like our Sun, will have a long life by burning their reserves of hydrogen and deuterium for billions of years to ensure the triumph of the king helium. And, as the concentration of helium increases during their life, the color of the star will turn yellow like our Sun. Then, when all its stock of nuclear fuel will finally run out, its color will turn red. And finally, the star will finish his career in a small star called red dwarf with a size comparable to Jupiter.